So let's start today's lecture. So yesterday, I introduced this general formalism of the topological recursion, starting from the data of a local spectral curve. And what I will do today is first give you a few examples of applications in geometry, and then try to really study explicitly what is hidden in this topological recursion formula and its connection with the moduli space of Riemann surfaces. So I will start with some examples. And the first one I will describe is the example of simple of its numbers. So I want to study the following problem. I want to enumerate covers of P1, the Riemann sphere, by some genus G surface. And what I want to do is to fix the type of ramification I can have for this cover. So basically, if I've got P1 downstairs, let's say that I mark infinity here. And I will look at the following problem. I want to cover this P1 by a genus G surface such that the cover is ramified over infinity with an arbitrary ramification profile, which I will call mu. So in this case, the profile would be 3 and 2. And apart from that, I allow only simple ramification points. So one type of such cover is this one. Yep. Yeah, where this point and this point do not lie above the same point here. So I've got 3 values downstairs of the P1 above which I've got ramification. So what I call mu, the ramification profile at infinity, is basically describing to you how many sheets of my cover coincide and how they do coincide. So I will use the notation that mu is a partition mu1. So let's put it this way. Yeah. It's the data of mu1, mu2, up to mu. And the index is what is called the length of the partition. And if I've got a ramification profile mu1 to mu length of mu above infinity, it means that above infinity, by this cover, I've got length of mu points, so as many as the number of elements here. And there is one point where you've got mu1 sheets of the cover, so mu1 branch of the cover which meets, which coincide, another point where you've got mu2 of them, and so on. So in this case, I've got a cover of degree 5, meaning that above a generic point, I've got 5 points of my cover which give the same image. But for above infinity, I've got a ramification profile of type 3, 2, which means that I've got actually only 2 points above infinity, one of which at which 3 sheets of my cover merge, and another one where 2 of them merge. Now, what I will study is the number, what is called simple Hurwitz number, which I call Hg mu, Hgn of mu, which is equal to what? It's the number of cover of P1 by a genus G curve with ramification of type mu above infinity such that the length of mu, so the number of points above infinity is equal to n, so this second index, and simple ramification points elsewhere. Yeah. Yeah, it's the same n. N. Sorry? No. Yeah. Yeah, I'm not specifying the degree. So the degree of this map can be anything. So it will just be given by the size of mu. Yeah. Yeah. So that's not what I put here. So okay, it might be, yeah.
Well, I didn't mu and I specified G.
Okay. But as far as I understood, you've got just one profile here. Yeah. You just have simple ramification points. Okay. Yeah, so here you can see that in all these primes, so people study this kind of enumeration prime, enumerating covering of P1 with some fixed ramification. Now, the way you sort these maps depend on your background, and you will get different generating series. Now, what I like to have is a generating series which is labeled by an integer g, and another integer which in general will have nothing to do with the degree, but it will have to do with the number of boundaries of my surface. So if you remember, in the case of maps, I was marking n faces, which was corresponding to the n here, but these faces, they could have an arbitrary degree. So they could have an arbitrary length, these marked faces. And the length of these marked faces is exactly corresponding to this mu1 up to mu L. And so I was not fixing them, I was summing over them. And here I will do something very similar. Yeah. So now, here I just said I have simple ramification point elsewhere, but by Riemann-Horowitz, the number of simple ramification points is, and my notation is, yeah, I didn't give it, 2g minus 2 plus n, yeah, plus the length, the size of mu, where the notation is that the size of mu is equal to sum over I equal 1 to the length of mu I. So the degree appears here in the number of ramification. Okay. Yeah. So now the question is, can I compute these numbers? And now the idea is, once again, that I will try to get it by topological recursion by building a generating series for this HGN. Then look at what happened for g equals 0 and equal 1. And then try to extract from that some local curve or global curve and run the topological recursion. Not over infinity. Yeah. 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 All right. Okay. Now, what I do is that I build some generating series for these numbers. So as I was telling you, what I will fix now is not the degree of my curve, of my map, but it's the genus and the n, which is the length of my partition. And I will sum over partitions. So I sum over a partition such that its length is fixed, equal to n. I give it a weight hgn mu. I divide by the number of simple ramification points. And what I want to do is to build a generating series for that. Sorry? Factorial, yeah. And I want to build a generating series for that. So what I will do is what I was doing before. Yeah, these ones, you mean, the simple one. Yeah. What? These one are not labeled. These one are labeled, and this one, yeah, and this one are as well. That's why you've got this factor. Yeah, yeah, yeah. So all of them. And so indeed, the one above infinity are labeled, and this will come here. So there is a labeling for each of the point of above infinity, and to each of them, I will associate a variable exponential x. So I make a product from I going from 1 to the length of my partition, so which is equal to n. Exponential mu I xi. So I've got a variable xi associated, xi associated to each of the points, but I want actually to have a symmetric function of the xi. So what I do is that I sum over a permutation of n elements, and here I put some sigma x index sigma of I. So I sum over a partition, meaning that I've got, when I say partition, it means that this is not a vector, but I've got an ordering in the mu's. To each of my point above infinity, I associate a weight exponential mu I xi. So you can think of the xi as a variable associated to the local degree of my map around this point above infinity. But I want to have a function which is symmetric in the xi, so I sum over the symmetric group here. The action of permutation of n elements. And this I call it W Gn of x1 xn. So since I spend quite a lot of time studying maps, you can see exactly the counterpart of this in the map case. The map case, I was enumerating maps of genus G with n marked faces, where each marked face adds a given degree, which corresponds to the mu1 to mu n here. And whenever I add a marked face of degree Li, I add some xi to the power minus Li minus 1. Here I'm making another choice, which is that if I've got mu I as the degree, local degree of the map around the point above infinity, I associate a weight exponential mu I x sigma I. What's wrong then? Yeah, I'm just using what is? So not an ordered partition, just a vector. Yeah. Yeah, unordered. Yeah. So here I'm just taking what is in the literature. Another way to state it would be to take a sum over vectors of size n and having just a product which would be obviously symmetric. Yeah, I agree. Yeah. And one way to think about it is to say that you wouldn't have any ordering the point above infinity. So these are a priori function of x1, xn. I mean, these are just generating series. And now the question is whether I can compute them. Now, first step is the following one. Can I compute W01 of x? Yeah. I think of it as formal Power series in exponential xi. Yeah. So in which case, you really recognize exponential xi to the power mu I. So it's exactly of the type that we had before. Indeed. No. Yeah, you wouldn't have a formal Power series even. OK, so what about W01? W01 of x, you can prove that it is solution to an equation, which is the following one: exponential x is equal to w 0, 1 of x, exponential minus w 0, 1 of x. So how do you get this equation? You get it by writing down a set of equations which are known as cut and join equation. These equations are concerned about the following fact. Here I've got a ramification above infinity. I can encode it into a permutation of the sheets of my cover here. So if you've got such a Hurwitz cover, you can associate to it a problem of factorization of permutation of the elements in the following way. When you've got a ramification above infinity, what does it tell you? It just tells you what happens if you go around this point above infinity. What you know is that you will have locally, so for this degree 3 case, so I've got this point which is above infinity, where the 3 sheet merge. And I look just at a point just next to it, and I wonder what happens when I go around it. If I start in one sheet of my cover, then I will go through a branch cut. So I start from one sheet here. I go to another sheet by crossing a branch cut. And what I know, because I've got a ramification profile 3, is that before coming back, I will have to cross 3 sheets, which are the 3 sheets of my cover here. Now you can associate to that a permutation of, if you label the different sheets of your cover from 1 to the degree of your map, which is equal to the degree of mu, then this can be mapped to a permutation of length 3 in this set, saying that I start from the sheet 1, then I go to another sheet which is I, and I1, and another one which is I2. So I can associate to this a cyclic permutation of these indices. I can do the same for each of the element above infinity. So here I would have another permutation which is just a transposition, I3, I4. And this gives me a permutation of 5 elements, which is the degree of my cover. So what I can do is associate to the ramification profile above infinity a permutation of the sheets of my cover, so permutation of the number of elements. And now the problem of finding a Hurwitz cover, so a cover of P1, which is ramified anywhere else, is telling you what? You've got this ramification here where you can, to which you can associate some I, J, K, L, M, so some permutation which has this type of decomposition into cyclic permutations. So one cyclic permutation of 3 elements, another one of 2 elements. And what you know is that above 0, you've got a ramification profile which is just 1, 1, 1. A ramification profile which is 1, just only 1, so it's not ramified, means that the corresponding permutation is just 1, 2, 3, so length 1 cycle to 5, which is equal to the identity. And so the problem of finding a cover is to find a sequence of permutation which correspond to simple ramification point. Simple ramification point means that you've got just 2 sheets which come together. So it means that you've got just a transposition. So you're looking for a sequence of transposition, tau 1, tau 2, up to tau 2g minus 2 plus n plus mu, such that when you go this way, this composition is equal to the identity, which is the profile above 0. So you can associate a problem of enumeration of factorization of a given permutation into transposition. And now what you can do is say, OK, what happened when I compose this first transposition with this one? I get another permutation. So I will get another prime of Hurwitz cover with another input here with one less simple ramification point. And if I do that for the case where here I've got n equal 1, which means that the length of my permutation is 1, which is the case where I'm fully ramified above infinity, meaning that I'm looking for some decomposition, factorization of a length n cyclic permutation into a product tau 2g minus 2 plus 1 plus n. You're trying to solve this prime for g equals 0, which is the case above. So here you put a 0. It gives you n minus 1. If you do that, you can wonder what happened when you act there. You see that it will actually give you a new permutation which has two components. And in some sense, it will cut your prime into two parts. And it gives you an equation exactly of the type of the Tutte equation. So I'm just getting an equation for the coefficient of my generating series as before. Sorry? Yeah, but it's the same. In the case where I've got just yeah. Yeah, OK. Sorry. Yeah, but it was the same here. Yeah. Yeah. So from this consideration, I get a relation for the H01 of mu with different mu's. If I write what it means in terms of generating series, it gives me an equation which, when I integrate it, gives me this equation for W01. So it's very similar to what happened for the map case, where I was looking for a combinatorial equation, this Tutte equation. Translate it in terms of generating series, it gives me an algebraic equation for W01. Now I've got an enumeration prime labeled by g and n. I know that for g equals 0 and equal 1, it gives me an equation. No question, if I run the topological recursion there, do I get the WGN, which I have defined in this way? And the answer is yes. And it was first proved by Enar, Moulassé, and Sarnouk. And it is the fact that if you run topological recursion for the curve given by this equation, so which I consider as a global curve, and there is a natural omega 02 on this one, then the omega gn of Z1 to the n built by the topological recursion is equal to this W gn of x of C1, x of the n, product over I equals 1 to n, dx of the I. For 2g minus 2 plus n, strictly positive. Now, I'm not telling you what I call this function x of z, but once again, the point is that these are defined as a series in exponential x, so these are just formal series. Now, the fact that you've got that if you look at W01, you get a solution to this equation, means that you can promote it to a well-defined function on the associated Riemann surface. And what I call Z here is a coordinate on this Riemann surface. Now here you see I don't have these indices for the local version of the topological recursion. The point is that in this case you just have one ramification point, so it's a pretty easy case. Most of the information is hidden in the involution around this branch point. So I will not prove this statement. I just wanted to show you an example of application which was a little bit between the case of maps, which is really an enumeration problem, a problem of combinatorics, and the kind of problem I will look at now, which will be problem more of the type of Gromov-Itten invariance, which is enumeration of maps from a genus G surface to some target space. So here in this case, I'm looking at specific maps, which are just covers. Yeah? No. So I mean, it's a theorem in the sense that it is proved. And one way to think about it is to say that this cut-tension equation for arbitrary G and N can be written down. They fix some relation between the H, G, N, which fix them. So you can map that to the definition of the topological recursion. But this map is not it's not a simple one. I mean, you cannot just say do as we did in the one matrix model in the random map case, just saying, okay, I've got this set of Tutte equation, and I just apply some projection operator, this residue, in order to get the topological recursion. Here it's more tricky. This is a more complicated transformation. And in particular, it takes into account the involution around the simple branch point of this curve, which is very complicated. But yeah, I mean, so it's not a theorem which is proved by checking order by order to some finite order. I mean, it's a theorem which is true completely, and it's just, if you want, just mapping equation to equations. And that's something which will be hidden in all this setup, which is that when you want to have a theorem saying that some enumerative series, generating series, is equal to something computed by topological recursion, basically what you want to do is to map some combinatorial relation specifying the coefficient of the expansion of this generating series with the definition of the topological recursion. And all the difficulty is in finding first which generating function to choose. How do I choose these weights here? And second, when I have that, how can I translate it directly into this topological recursion relation? Yeah.
When you say that the starting point is the data.
Yeah.
My question is something completely developed to do that starting point.
So in this case, I couldn't, because I will have a curve which has genus 0. And I told you that there is a unique W02 on this curve. So the condition I gave you for the type of omega 02 I can take on a global curve fixes it completely if the curve has genus 0. So in this case, I don't have any freedom. Yeah. Not far from that, but no, not that directly. I think it does, actually. If you fix, I don't think, Paul, maybe you've got an idea on that? I think it does. So, No, the question is whether cut-and-join fixes completely the HGN, the Hurwitz number. I think it does. Yeah. The point is that so you've got a set of equations which you know has a unique solution. It doesn't mean that you know how to solve it. Yeah. Yeah. So that, yeah. And basically, you transform this constraint into a constraint which is solvable and a solution to this constraint. But yeah, I mean, the difficulty is that even if it fixes it, in some sense, you might have a kind of triangular system, but you don't know how to solve it. If you just look at the cut-and-join equation, it's a tricky transform which allows you to solve it. Yeah? This is, that's another statement. So yeah, it does, but in a tricky way.
Then the theorem is done.
Yeah, but you would go the other around in the sense that, as Paul was saying, and as we could see, so in the case of maps, we had this Tutte equation, which gives you this loop equation. From that, we could extract the topological recursion by basically forgetting about the polynomial p and some part which we didn't like. Now, indeed, the topological recursion produces for you the WGN, so they satisfy these loop equations. Now, in order to recover this loop equation, it's not that easy if you just have the topological recursion. You have to work a bit. And yeah, I mean, there is some structure in the recursion which is like that. So in principle, yeah, you would be able to go back, but that's not an easy step. And that's not something you really want to do. I mean, usually we do the other around. We've got a set of combinatorial identities, and we want to solve them. I'm coming from physics, so I want to compute things. So I don't know. Yeah. Yeah.
In my course, I talked about the really simple orbits.
Yeah.
Simpler than these with no U. It's all simple. Counts the term with a linear term.
Yeah.
Sort of a coefficient of E.
Exactly. So what you would do,
You get that out of these formulas is there any
compute some residue.
No, you can get it for a given G.
Yeah, that's the. So here you see all the trick about choosing which parameter to choose in order to define your generating series. And so that's not an easy thing. So what you would do is a sum over G and N, I guess, such that you've got the degree which is fixed. I mean, I didn't try to do it. That's a good question. No. No, because the. Yeah. Yeah, but after that, in order to recover your relation, you would have to resum, I mean, some large number of terms which depend on the degree. So what would be nice is indeed to have a kind of combinatorial way to go from this kind of recursion to your recursion. I mean, yeah, that's something we should discuss. But indeed, I mean, that's something very important to keep in mind, which is that in all the example I will show you, basically, I choose to fix from the beginning some label I will fix for defining my WGNs. And I will sum over some other degrees of freedom. There are many, for the same numbers, there are many generating series which have also some very nice structure when you sum over other things, for example, some fix the degree and sum over G and N, which has a nice structure. But this is not what I will discuss today. I mean, this is not something which will be taken into account from the topological recursion that directly. Is there any other question? Yeah?
Here you are using monomial.
Yeah. Yeah, but for the it would be another representation of the recursion if you want. So the recursion encodes the combinatorial relation between this object by just choosing this specific symmetric polynomial. Now, I could take some other symmetric polynomial. I would translate exactly in the same way this cut-and-join equation into some, not algebraic, but some relation for this function. And They will not take the form of the topological recursions. That's my point. But the information, yeah. But now, in this case, it's OK. We can do it. So, I mean, that's something I will not discuss in these lectures. But the topological recursion, in the cases where you've got a global curve, it's expected to give you an expansion in some parameter of tau function of associated integrable hierarchy. And one way to go from 1 to 0. So after that, the choice of polynomials that you've got here, in some sense, it's a choice of basis for the time of your hierarchy. So these are just changes of basis. I mean, in this case, we can do it explicitly. No, in many cases, it's more complicated. Is there any last question since I'm here? No? Yeah? Which one? Which genus? Yeah. So you want to remove that? No, OK. No, not at all. No, so it's the other way around. If you think of it as a, so this you can think of it as sigma being the locus of x and y in C2 such that this equation is satisfied. Now, when I do that, I choose some x and y. So I've got a parametrization of my curve. Omega 02 is an object which is intrinsically associated to sigma. It doesn't know about x and y. So yeah, it's the other way around. Omega 02 doesn't know anything about x and y. Omega 01, in some sense, knows about this relation. OK. OK. So if we can keep on going, I think I will finish this first lecture just by giving you another nice example of application which will go in the direction of considering Riemann surfaces. So I will consider the computation of the volume of moduli space of bordered Riemann surfaces. So here is the kind of problem I want to look at. I consider the space of genus G Riemann surfaces with one boundary. And I ask this boundary to be a geodesic of given length L. So here I just have one boundary of length L1. And so I've got a genus 2 surface with one boundary. I will say that it belongs to some moduli space of genus 2 surface with one boundary, whose boundary length is equal to L1. And in general, I will look at some moduli space of genus G Riemann surfaces with n geodesic boundaries of respective lengths L1 to Ln. So when I'm talking about moduli space of Riemann surfaces, I think of the underlying topological surface. But in addition, I equip it with some complex structure, which give it the structure of a Riemann surface. So I will not discuss the detail of the construction of this moduli space. but I will give you a recipe to define this volume. So I want to know what is the volume of this moduli space if I fix n, g, and the length of the boundary. So in some sense, I want to know how many surfaces of genus G with n boundary was boundary length is equal to L1 to Ln I can build for fixed G, n, and Ls. So these are, yeah, sorry. So I look at 2G minus 2 plus n strictly positive, and in what I'm doing, I will just consider hyperbolic surfaces. So I've got an hyperbolic metric.
So you're fixing curvature minus 1.
Yeah, I'm just, yeah.
So you can't rescale the L.
No.
So you're fixing the
Yeah, otherwise, I mean, you would lose all the information. Okay. And so I want to compute a volume over this space, but in order to compute a volume, I need a volume form. I need some measure on this space. And in order to describe this space, one easy way to do it is to say, okay, I've got a Riemann surface with a boundary. Now I could decompose it into pairs of bands. And then say, okay, if I want to build an element in this set, I just need to build elements which are pairs of bands and glue them together. The idea behind that would be that the simplest element would be the case where I've got G equals 0 and equals 3, which is just the moduli space of pairs of bands with given boundary lengths. And something you can prove is that this moduli space has dimension 3G minus 3 plus n. So in particular, it implies that the dimension of M03 of L1, L2, L3 is equal to 1. Is equal to 0. So here you've got really an enumeration problem. And what we will do is normalize this, the volume of this space. I mean, this gives us that the volume of this space will be normalized to be equal to 1. Now, when I'm saying that I'm decomposing it into pairs of bands, in the pair of band decomposition, what you can see is that there will be there are 2G minus 2 plus n pairs of bands. In a decomposition. Of some surface of genus G with n boundaries. So let's look at this example. We've got 1, 2, 3 pairs of bands, and we 1, 2, 3, yeah. And let's compute it. So we've got 4 minus 2 plus 1, which is equal to 3. Now that's the first thing. And now let's count the number of curves along which I glue these pairs of bands. So they are glued along 3G minus 3 plus n curves. So once again, let's compute it. 1, 2, 3, 4. 3G 6 minus 3 plus 1. OK, that's fine. It's equal to 4. So the math is right. Now, you see that this 3G minus 3 plus n is actually equal to the dimension of this moduli space. And the idea behind that is that in order to get an element here, I just need to take 2G minus 2 plus n pairs of bands. For choosing any of them, I've got a dimension 0 space. So I don't have to bring much information there. So the information I need now is just to know how I glue them together. So what I need to know is that for each curve, so for each gamma, I need to know the length of this curve. And I need to know as well how I will glue the two copies of this curve coming from the two different pairs of points in my pair of point decomposition. So I need some twisting parameter, which I will call theta gamma, which tells me if I start from one pair of points on one side and another one on the other side, each of which have a mark point. When I glue it together, I can choose the twist I put when I glue them together by the respective position of these two mark points. And so it's a twisting parameter which just lives on the circle S1. So you can think of it as being theta gamma being an element of 0, L gamma. Yeah. Sorry? Yeah, that's a den twist, yeah. So you can, so that's a twisting parameter which tells you which is the den twist that you use when you act on there. But yeah, don't want to enter. Yeah. So I've got two parameters for each curve, but these are two real parameters. And when I was talking about dimensions, these are complex dimensions. So the count is right. It's 3g minus 3 plus n times 2 real parameters, so it's 3g minus 3 plus n.
Before you said 0, 3, L1, L2, point.
Yeah.
But now you're also marking the point on each.
Yes.
Is that the same?
Yeah. So this is the moduli space without marking. So a priori, you would have some S1 to the power 3, which would come from there. But you can divide by by some S1 action in order to get something which is well defined. OK, yeah. Another way to say it is that if you look at the geometry of your pairs of points, there are some specific mark points on each boundary which you can use. Yeah, yeah. I mean, yeah, that's the right answer. So there are some generic ones. So if you've got an hyperbolic structure there, with the hyperbolic structure, you can find some very peculiar geodesics, for example, geodesics, which are orthogonal to a pair of boundaries, and you can use that as reference points for having a marking on your boundary. Yeah, but they have some symmetry. There is symmetry there, so there is no issues there. I mean, it's just that, yeah, you can decompose your pairs of points into two pentagons which are glued by half of the edges, hexagons which are glued by half of the edges. So, OK. So here I just describe roughly the way we can look at this moduli space. So indeed, this description depends on a choice of pairs of points, which is not unique. So that's really a local description, and you would have to mod out by some group action. But the whole point is that I can define a volume form on MGN L1 to Ln in the following way. I define the Weil-Petersen volume form as being equal to just the natural volume forms that you can imagine in these coordinates. For each curve gamma, you take the one form dl gamma wedge d theta gamma. And you sum over the gamma which cuts sigma gn in pairs of bands. Sorry, it's a product. In pairs of bands. So it's a product of 3g minus 3 plus n to form, to real form. So it's a 3g minus 3 plus n. 6g minus 6 plus 2n form, which is exactly what you need in order to integrate over some space of the dimension 3g minus 3 plus n. Yeah? Was there a question? No? Yeah? So the volumes that you will compute. So indeed, this should depend on the pairs of band decomposition, but actually the right way to define this moduli space is by considering the space where you would have pairs of band decomposition and modding out by action of the mapping class group, in particular, which exchange your pairs of band decomposition. But you can use this volume form so you can use this volume form, which is well defined on the Teichmüller space, in order to define a volume form in this moduli space where you mod out. So that's why I said I didn't want to enter the detail. I just want to give you the idea. Sorry? So I will put 2 pi here. Yeah, sorry. I should put, sorry? It's 2 pi. I will take 2 pi here in the following. Yeah, sorry. Yeah, so there is, yeah, but I don't want it. No, it's TL. It's TL here. No. What? No? Why? Why do you expect the law? I mean, am I wrong? Don't think so. LE, sorry? Yeah, but I take theta to be in 0 to pi. Yeah? Ah, okay. No, but no, that's the volume form that you take. So you wanted to write it in this way, exponential log. I mean, to identify the 2 parts, right? I mean, yeah. That's the volume form I'm considering. So, yeah, L is positive. Yeah. Okay, yeah. And so I define the volume of my moduli space to be just the integral over this moduli space of the Zweilig-Petersen volume form. What time is it? Yeah, and maybe now I will write the statement before the break. And now the statement is that if you take this W Gn of L1 Ln, multiply by a product from I going from 1 to n of Li exponential minus Ci Li d Li, and I integrate all the lengths to be in R plus. So Laplace transform with respect to this length. So I get a function of the zi's. Which is just defined in this way. And now the claim is that omega gn of z1 cn, which is wgn of z1 cn product over I ranging from 1 to n of dci is given by topological recursion on a global curve, which is the curve y is equal to 1 over 4 pi sine 2 pi square root of x, where z, the z which I'm using here, is given by x square is equal x square x of z square, the x which is here is equal to z. X of z is equal to z squared, sorry. So now if I would write it in this coordinate z, the curve is the one where you've got omega 0, 1 of z is equal to sine 2 pi z divided by 4 pi times dx of z. So I've got a 2 here, z dz, and omega 0,2 of z1 z2 is equal to dz1 dz2 divided by z1 minus z2 square. And once again, this is a case where you just have one simple ramification point, which is located at z equals 0. And your omega 0,2 is completely fixed by the fact that you've got a genus 0 curve. So theorem, this is proved by Ena and myself, but I will tell you about the proof, and the proof heavily relies on great work of Mirsarani in the study of these moduli spaces. So that's what I will tell you just after the break. So what she did find is that by hyperbolic geometry, she could find some relation between these VGNs, these volumes. And if you apply this Laplace transform, this gives you directly the topological recursion. So she did all the hard work. We just computed the Laplace transform. So the answer, the good thing is that, and you could see already from the Mirsarani point of view, these VGNs, these are polynomial in squares of the length, with coefficients which have a nice form in terms of integral over the moduli space of Riemann surfaces, not bordered one, which is what I hope to discuss in the second part of the talk. Okay, so let's have a 5-minute break. So here my claim was that if you take this volume of moduli spaces, Laplace transform it, you get this WGN, you get some WGN, which are function of Z1 to Zn, which actually are given by topological recursion on a very specific spectral curve. Maybe to make the connection with Hurwitz number, so you see that the way I would like to think about it is very similar to the generating series I did write down for Hurwitz number, which you can still see here, which was that I had this sum over mu, some weight which depend on mu, product over I, exponential mu I xi. Yeah? Yeah? This one I will tell you exactly how I do. But the hard work has not been done by us. It's been done by Mirsarani. There is another recursion found by Mirsarani. Exactly. Yeah. And the idea is always the same. You're looking for a first recursion which encode the geometry or the combinatorics there. And you want to encode it in generating series, very specific one, in order to put it in the shape of the topological recursion.
So previously there was
Yeah.
now there's something else.
I will remove some pairs of pants. So yeah, what I wanted to point out is that in the Horvitz number case, I had this kind of generating series, which now, if you think of mu as being a discrete equivalent of the length, takes exactly the same shape as this Laplace transform. It's a kind of discrete Laplace transform, and here I'm doing a continuous Laplace transform. What was h of mu here is now this v of L, and what was this exponential mu I xi is now this exponential minus zi Li. So actually, the shape of these generating series are very similar, just that on one side I've got discrete possible lengths, and here I've got a continuous possible length. Okay. Now, what about the proof? So I will not give you the full proof. It would be too long, but I will give you the idea. And so, yeah. I will do it. It's similar. So how do you define cotangent on this moduli space? But it's the equivalent. So yeah, I mean, most of what I will tell you is coming from Mirsarani's work. And in particular, something which will be very useful is what is known as Mach-Chain identities, and actually generalization of Mach-Chain identities by Mirsarani. So the idea is the following one. I consider genus G Riemann surface with possibly many boundary components, at least one, of length L1. And I ask the following question. I'm sitting on the boundary here. So I did choose a very specific boundary. And I'm throwing a geodesic orthogonally to this boundary at one point, which I choose. And I'm wondering what it can do inside my surface. So it can do many things, but for example, what it could do is go around there and come back to the same boundary at a different point. If it does that, what you can do now is to look at a small neighborhood of your boundary union this geodesic. So just go around here, come back here, and it comes back here. And the same thing on the other side. Come back here. Now, if you look at it carefully, if you would deform these two green paths, you can deform them to paths on the curve which look like this. And actually, there is only one geodesic representant in this class of paths, which exists, so I could take it. And now I could look at the pairs of points, which is defined in this way, where I've got two boundaries components which are given by this, the representant of the class of these two green paths as a geodesic, and the original boundary. So what I did do for you is by just throwing geodesic inside my surface orthogonally to the boundary at one point, it defines for me pairs of points embedded inside my surface with boundary geodesics, such that one of the boundary components is the original one. So here I just gave you a very specific example. You could have some other thing which might happen. You could have, for example, that your geodesic could go away there and reach another boundary component. And you play the same trick. Yeah, I should take another color. And what you will see if you do the drawing appropriately, up, come back here. Then it defines for you, once again, a pair of points embedded in your surface. But no, this pair of points have two boundary components in common with the boundary component of your surface and another one which is inside. So one way to draw it is to say that I have two boundary components here. I've got the genus 3 surface. And I've got one pair of points embedded into this surface, such that two of its boundary components are common. So one of them is the original marked boundary component I use for throwing my geodesic. Another one is another boundary component, and the last one is inside my surface. I know you can start wondering what happened when you browse the whole boundary like this, just changing these points. And that's exactly what McShane is doing. And she's enumerating all possible configuration which can happen. So you see that if I just move a little bit here, I will not change the pair of points that I define in this way. And in some sense, there is an interval around this point such that if I throw a geodesic orthogonally inside this interval, I will get exactly the same pair of points by just this procedure. Now, if you do that for any point, you get a decomposition of the boundary into arcs of finite length and some infinite set of points which give you some length 0 interval, so some measure 0 set. And now, McShane identity is just telling you that the length of your boundary, L1, is equal to the total sum of this arc, each arc corresponding to a pair of points embedded into your Riemann surface. So you just write L1 is equal to sum over, sorry? Sorry? So, no. Which arcs? These ones? So the pair. No, there are finitely many terms here. I mean, no, infinitely many, which will be labeled by the length of the arcs here, L alpha and L beta. Yeah. 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 Which correspond to different lengths of the boundary for your pairs of points embedded. So it's a sum of pairs of points embedded into your surface. They could have arbitrary lengths. No. Yeah. 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 Many arcs of this type. So yeah, there are infinitely many. No, there are infinitely many arcs. Yeah. Yeah, it's uncountable, but you've got it defines a. Okay, if you look at the. It's a continuous set. So you define a contour set on this boundary. Yeah. So the question is it about the arcs or the number of? So the arcs are uncountably many, and there is uncountably many points which give you a measure zero set. So yeah, and you've got the sum. You get that the length of your boundary is the sum over all these arcs, which are pairs of points P embedded there, and there is some function of P, which is the length of these arcs. Now let me be a bit more precise by saying it in this way. There are two things which might happen. I did to you in this case. Either the pair of points has only one boundary component in common with the surface that you start from, or it has two. So in the first case, it's a sum over pairs of geodesic alpha, beta inside your surface, such that alpha, beta, and the first boundary component, which I will call delta 1, bounds a pair of points. Inside sigma. And here you've got a weight which is just given by some function of L1, length of alpha, length of beta, which you can compute. And the second case is a case where you've got another boundary component which is there. So I consider sigma gn, sum over I ranging from 2 to n, of sum over geodesic alpha, such that delta 1, delta I, and alpha bounds of pair of points. And you've got another function which I will call R of L1, Li, L alpha. Yeah, sorry. So I'm writing a sum over geodesic alpha and beta inside my surface such that the first boundary component together with alpha and beta. So I choose a boundary component to start with. I call it delta 1. It's a boundary component, a connected component of the boundary. So here I've got two boundary components for my surface, delta 1 and delta 2, let's say. And here I'm making a sum over alpha and beta, which are these curves, which are geodesic inside my surface, such that alpha, beta, and delta 1 bound a pair of points inside my surface. So that's the first case, and I've got a weight which is given by a very specific function, which depends on the length of the respective boundary components of my pair of points. Now I've got another thing which might occur, which is that I could have a pair of points embedded in my surface such that two of its boundary components are a boundary component for the original surface, one of them being alpha, the other one being one of the n-1 remaining boundary component. So this is delta 1, delta I, where delta I is one of the n-1 remaining boundary components. So I've got my surface with n boundary component, which I label by delta 1, delta 2, delta 3, to delta n. So I choose this, yeah, because I want to have an equality which, so I want to have L1, which is the length of delta 1. Yeah. No, but actually that's a very important point, which is that when I'm doing that, I'm breaking the symmetry of the problem in the sense that I'm saying that the first boundary component is more important than the other one. So I choose it. I completely broke the symmetry of the prime. And that's what will be reflected in the fact that the formula for the omega gn is not symmetric, even though the result is a symmetric function. So I'm breaking the symmetry by choosing this delta 1 component. Then alpha is a geodesic inside your surface such that alpha, delta 1, and delta I bounds a pair of points. So if you've got a geodesic going from delta 1 to delta I, you just draw a curve in the neighborhood of this geodesic, and it gives you a geodesic inside your surface, which it gives you a path. It gives you a cycle such that in this class, you have a unique geodesic which bound a pair of points with delta 1 and delta I. So just think of this picture. You just draw your blue line, and you take it away. And it will give you something which will go around here. OK. And so this comes with another weight, which is a function of the length L1, Li, and the length of this inner geodesic. OK. So now, if you remember, one of the interpretation I had for the recursion, which was this, I said that you can interpret it as degenerating your surface. Here you've got exactly the same. Sorry? Yeah? So L1 is equal to this big sum. So I'm just writing a refined version of this one. Here I didn't say what is the function I associate to P. So here what I say is that this function of the pair of points, you've got two possible cases. One case where you've got a pair of points where you just have one boundary component coming from the outside, in which case it's just given by a fixed function f of the length of your of L1, L alpha, and beta. And the other one is another function, in the other case, of the length of this boundary, and this one. A pair of points, inside sigma with embedded in sigma. So nobody, I mean, this is the right formula. This was just a short one. So this was the sum of the pairs of points embedded into sigma. Yeah. No, pairs of points. But yeah, I mean, that's the right formula to think and to have. No, you don't know what this is. But now I want to integrate that over the moduli space. Yeah. So in order to write down an equation, you don't need to know it. What you need to know is some properties. For example, for this case, what you need to know is that it will be a function of the sum. It will be a combination of function of the sum and the difference of the lengths in order to be able to integrate. But a priori, you would not need an explicit formula for them in order to get a nice relation for the volumes. So it's a function. So at the end of the day, you would be able to write it as a function of two variables. But yeah, I will not give you the formula for them. But one way to think about this is that from my perspective there, this function exactly encodes the definition of my curve here. Yeah. You can think of it in this way. Sorry? Yeah, so this is a sum of, it's hidden here. But yes, this is one way to think about it. So now, I will be very sketchy because I don't have time and I don't want to spend too much time explaining that. But the idea is the following one. The left-hand side, now I can integrate along mgn of L1 Ln omega by Peterson of L1. So I'm just integrating the function L1 over this moduli space. L1, I can take it out. So that's just equal to L1 times VGN of L1 Ln. What about the right-hand side? Now, here I will be adding a lot of things, but the idea is the following one. If I fix one embedded pair of points here, the idea behind this procedure is that if I want to integrate over all these surfaces, one way to think about this integral over mgn bar is that you will decompose into integral over the surface, which is obtained by removing one pair of points, and you sum over all possible pairs of points which are embedded, so all possible ways of removing a pair of points. Now you need to give a weight to the pair of points that you remove, which would correspond to summing over a set of configuration of pairs of points. And this is given to you by this function f, or r. So the idea is that the right-hand side, you can write it in the following way. If you want to integrate the right-hand side along mgn of L1 Ln, you write it. So I make a sum over alpha and beta such that all this is satisfied. And now I want to integrate this over mgn bar. And I say, OK, so I will integrate using this coordinate along L alpha, so possible length of alpha, possible length of beta, and then I just integrate over the moduli space of bordered Riemann surfaces, which are obtained by removing this pair of points, with a factor of which comes also from integration of theta there. So you will get at the end of the day something like sum over alpha beta. Yeah, sorry. Omega by Peterson. Oh, so I want to integrate the right-hand side, which is a function on this moduli space. Yeah. No, yeah, that's, yeah. Let's put a star. So this was the integral of the left-hand side, which is an obvious formula. Now, in order to integrate the right-hand side, what you say is that the integral will be equal to the integral over possible length here, integral over possible twist angle here, and then integral over what is left. And what is left is the integral over the moduli space of bordered Riemann surfaces obtained by removing the pair of points. And so it gives you different configuration. So it gives you integral over L alpha, L beta in R plus square. Here you will have some L alpha, L beta, f of L1, L alpha, L beta. dl alpha, dl beta. And what is left is the volume of sigma minus the pair of points, which is something you have seen already. So many things might happen. First, I could not disconnect my surface when I remove the pair of points. So it will be, I will get a genus G minus 1 surface with n plus, so I started from n boundary components. So with n plus 1 boundary component of respective lengths L alpha, L beta, L2 to Ln, plus sum over G1 plus G2 is equal to G, A, B is equal to 2 to N, just the stable part, of BG1 cardinal of A plus 1, L alpha, LA, BG2, B plus 1, L beta, LB. And here I'm saying fully stable, meaning that I do not allow either. So before I was not allowing any V01. Now I'm not allowing either any V02, because the V02 is coming from this part. So now if I remove a pair of points in this way, what is left here cannot be a cylinder. The case where it could be a cylinder is basically encoded in this second type of constraint. So it's sum over alpha, and you just do the same thing. L alpha in R plus. L alpha, the L alpha. Sorry? Yeah, I'm doing the second one. Sorry? Yeah, sorry, yeah. Sum from I from 2 to n, sum for alpha such that alpha, delta 1, and delta I bounded pair of points. And here I've got some R of L1, Li, L alpha. And what is left when I remove my pair of points is Vg. And I remove one boundary component by doing that. N minus 1, L alpha, L with the set 2 to n, to which I removed the ith boundary component. Yeah. This, it's because I've got to take into account the twisting parameter here. Yeah, so no, actually, in order to have the, yeah, it should have been in between 0 and L alpha. Yeah, sorry for that. OK. So now I've got an equation, Vgn times L1 is equal to this sum, which looks very similar to the topological recursion. You've got the same terms. So this was proved by Mir-Sarani. I mean, it's a very nice induction formula for these volumes. These functions actually are nice functions. Actually, their derivative are nice functions. They are things of the type 1 over 1 plus exponential L1 plus L alpha plus L beta. Yeah, OK. But yeah, I don't want to write it. So you can write it just as a simple rational function in exponential of linear combination of these lengths. So these are very nice objects. So what cannot cure it? So here it's L alpha, and here it's all the Li's with I be Lj with j being between 2 and n, but I remove the ith one. So here I've got my sum over I, and here I remove the ith boundary components. So we've got this very nice formula, which if you want, you can think of it as Q-tangent. You just remove your pair of points. But it's very similar to Q-tangent, a continuous version, saying that what happened when I have what can happen to a pair of points? I've got a length here and two other lengths here. I give it a weight. In the Horowitz number case, the Q-tangent was telling you, I've got one partition here. What happened when I cross, when I compose with a transposition? It's the equivalent of a pair of points. It can decompose it into two other permutations of different lengths. So it gives you the weight. And it gives me this very nice induction formula. Now, the only thing we did with Bertrand and R is just take the Laplace transform of this equation with this definition. It gives you directly the topological recursion formula. So this recursion is equivalent to the topological recursion in this setup. So out of that, yeah, you can see that. Yeah, but this I will not have time to do it today. So the way you do it from Mir-Sarani's side is quite a long story. Now, if you go to this side, you're doing a Laplace transform. By topological recursion, what you will find out is that the omega gn, these are polynomial, and we will see that in the next lecture. Oh, yeah, maybe we can see the beginning today, but this will be for this curve, this will be polynomial in inverse powers of z square, of zi squares. So you will have that these are polynomials in inverse power of zi square. If you invert this Laplace transform, it tells you that you've got polynomials in square of Li's. And from a general procedure I will give you, the coefficient of this polynomial is given in terms of intersection numbers. And I will start doing it right now, I think, if you agree. Is it OK? Yeah. So we get them as intersection numbers, but these intersection numbers are well-known numbers. So this will be just intersection of psi classes. For example, if you take g equals 0, arbitrary n, this will be written in terms of multinomial coefficients, combination of multinomial coefficients. Yeah. Yeah, I don't want to. Yeah, but I don't want to state too much. But basically, the function f, what is important is that if you compute df L1, L alpha, yeah, we'll write it here. df L1, L alpha, L beta over dl is a nice function. And here I'm not exactly sure of the formula. I think it's something, so maybe somebody in the audience know it by heart. I think it's something like that. L1 minus L. You remember, Paul? No? I mean, I'm not sure. But it takes this form. It's a sum of two terms which are written as 1 over 1 plus exponential of something, a combination. Sorry? Yeah, yeah. Yeah, but I guess that's not the kind of answer François wants. So, yes, sure. So Max chain identity, the original one, so I didn't say it, but it's considering the same kind of prime, but now where you've got a torus with one nodal point, where, with one point which you can think as the length L goes to 0 limit. So in which case you don't have much choice. You will have just one type of pairs of point embedded. So in this case, it will be a sum over geodesics gamma, which are inside your torus. And that's the original Max chain identity. So Mirsarani just made a huge generalization of this statement. Yep. And that's a very non-trivial result in the sense that, yeah, you're writing L1 as a very complicated function. And one way to think about it is that you did find that this very complicated function is constant on the moduli space of bordered Riemann surfaces. So if you move inside this space, this combination is constant. OK. And so indeed, this function f and this function r, which I don't want to write down explicitly, they encode why we've got this sign which appears in the curve. OK. So now I hope it gives you some taste of the kind of geometry or combinatorics hidden behind the recursion in different examples. And now I will tell you how it's related to the moduli space of Riemann surfaces. And for doing so, what I will do is just consider the very simple case where I've got just one branch point, n equal 1. I take omega 0, 1 of z, to be equal to 2z squared dz. So all the hk's which I introduced earlier are vanishing, except the first one, which is equal to 1. And omega 02 of z1, z2, which is equal to dz1, dz2, c1 minus c2 squared. And I compute the topological recursion for this case. And this is a very fundamental example. This is a case which seems very particular and very simple, but actually it has almost all the information about the topological recursion. Yeah. Sorry? It's the number of branch points. So in the local curve, that's what I said, it's the number of disks I have, so it was the number of branch points. So here I just have one, that's why I don't put any index I here. So yeah, I will come to that, but basically it would be related to the enumeration of ribbon graph. So what you will get will be intersection number on the moduli space of Riemann surfaces. And so it will be a sum of a ribbon graph. So it's another moduli space, which I will consider. Okay, but yeah. Kontsevich matrix model. Sorry? Yeah. So this is related to the matrix area function of Kontsevich. And basically, we can build almost everything in the topological recursion out of that. But so, yeah. How much time? Yeah, I will start the computation. And what I will try to end up with at the end of the day will be to show that the recursion in this case is equivalent to some Virasoro constraints. OK, so we start from there. And I just want to write down the topological recursion. So do you remember I had this kernel, K of C0C? And here I've got something which is very explicit. Wanted to compute the integral from z to minus z, omega 0 to, yeah, I'm sorry, I'm using z where I should use zeta if I wanted to be consistent with the previous sector. So yeah, 2 times omega 0, 2, so it's 4 times z squared dz. Now you can compute it, and you get that it is equal to minus d0 divided by 2z, z0 square minus z square dz. You just plug in this expression, you integrate it from z to minus z, and you get this equation. OK. Now, I want to plug it into the topological recursion. What I will do is that I will make an ansatz, which I will prove by induction in the process, which is that the omega gn of z1 to zn. Yeah. Done? Is there a question? Just tells you that there is only one branch point. In the local curve, it was the number of omega 01 I had to consider. If you remember, there was some index I here inside, ranging from 1 to n. And so there is only one disk here. I mean, the point is that the curve associated to that is the curve y squared is equal to x, which has only one branch point. So the ansatz is that these are actually differential indices which have poles only when z goes to 0. For 2g minus 2 plus n strictly positive, in which case I can write it as a series expansion, sum over k1 to kn, ranging from 0 to infinity. And I write it in this way. Some coefficient ck1 kn g, product from I equals 1 to n, 2ki plus 1 double factorial dzi divided by zi to the power of 2ki plus 2. So I will prove actually I can prove by induction using the topological recursion that it takes this form. And now I will translate the topological recursion into a recursion which tells me which are the coefficients. So it's a baby example compared to the preceding one. So the preceding one was a bit like a deformation of this one. If you look at the sign and you make an expansion when z goes to 0, this is the leading coefficient. Yeah. 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 Yes. Now, just write down the residue formula. Z0, C1 to the n is equal to residue, in this case, it's only when z goes to 0, of this kernel. So I've got a minus sign in front. dz0 divided by 2z, z0 square minus c squared dz. And now I've got the usual omega g minus 1 n plus 2 of c minus c, c1 to n, plus some of our stable terms, g1 plus g2 equals g, ab is equal to 1 to n, omega g1 a plus 1 of z, ca, omega g2 b plus 1 minus c, cb. Now, now that I have this formula and I make this ansatz, the only thing I will do is make an expansion of this when z goes to 0. And actually, what I will do is also make an expansion in z0 to the n in order to recover this coefficient. So if you plug this expression in this formula, and you look at the coefficient of z0 to the power 2k0 plus 2, at the coefficient of the product of zi to the power 2ki plus 2, gives you an expression of this ck1 to kn of genus G in terms of other ones. Now, the way you do it is very simple. The only thing you need to do in order to proceed is the following thing. You want to compute the residue when z goes to 0 of this function. So d0, it can go outside. And what is left is 1 over z times this. This, when z goes to 0, you can think of it as a geometric series in z square. So I will write it as sum over k, ranging from 0 to infinity, of z to the power 2k divided by z0 to the power 2k plus 2 times 1 over 2z dz. So I'm just expanding that around z equals 0. Times. So for the moment, I will not write this part, so I will just look at this, and I make an expansion in C. It's sum over d1, d2 from 0 to infinity, sum over k1 to kn, ranging from 0 to infinity. The coefficient is c, g minus 1, d1, d2, k1, kn. And it comes with what? So the two first ones, they correspond to z and minus c. So I get a 2 d1 plus 1 double factorial, 2d2 plus 1 double factorial divided by z to the power 2d1 plus d2 plus 4. Now I've got a dz times d minus e, so I've got minus, yeah, I shouldn't write it in this way, so let's write it as dz times minus dz. And what is left is just a product of these monomials in K. And what I will do is that I will not write them down just by writing what I'm looking for, which is just fixing the degree of the monomial I consider in the zi's to be equal to K1. So I want to have CG K0, K1 to Kn. And I sum over K0 only 2K0 plus 1 double factorial dz0 divided by z0 to the power 2K0 plus 2. So what I'm computing is just, I'm just fixing the coefficient I'm choosing for all the Ki's except for the first one. I'm still summing over the first one. Or you can think of it as taking the residue of this when z1 and zn up to the n go to 0 times the I to the power 2ki plus 1 divided by a combinatorial factor. So I get an equality of this type. This sum is equal to that plus another term, which is a sum over stable term. And here you've got exactly the same thing. It's CG1 D1 KA times C G2 D2 KB. And here I just have the same factor, 2D1 plus 1 double factorial, 2D2 plus 1 double factorial divided by C to the power 2D1 plus D2 plus 4 dz times minus dc. So no, I just have, yeah. Just have 2 minutes left. And so now what I am doing here is that I'm translating this topological recursion formula into an induction for this coefficient. Now what's going on? When I select some K0 here, I'm selecting the degree in 1 over Z0 square here. What does it do? It fixes K here to be equal to K0. So it fixes the K here. And my residue is doing only one thing. The residue, when Z goes to 0, just gives me some delta. A priori, it's delta K, but K has to be equal to 0. So it's delta K0. So I need to have that 2K will cancel the 2D1 plus D2 plus 4. So it means that I need to have that K0 is equal to D1 plus D2 plus 2. And that's the only use of this residue in the topological recursion. If you do that, then it gives you immediately the formula, which is the following one: CK0, K1, Kn, genus G is equal to, so you will have the minus sign here is cancelled by the minus sign here. You've got a 1/2 for the first factor. So it's 1 over 2 Cg minus 1 D1, D2, K1 to Kn. And you sum over all possible D1 plus D2 is equal to K0 minus 2. And you've got a combinatorial factor, which is 2D1 plus 1 double factorial, 2D2 plus 1 double factorial, divided by 2k0 plus 1 double factorial plus this part. Yeah, I'm sorry. Here I've been a bit sketchy in the sense that I'm saying that this is, actually this is true only for 2g minus 2 plus n strictly positive. For g equals 0, you see that you don't have that because that's exactly the Taylor series expansion I did right on before. So you've got this omega 0, 2, which is written here, which doesn't satisfy this property. So actually here I should remove from this table sum all the cases where I've got g equals 0 and 2 terms here. This is exactly what I did for defining this fully stable sum for Mir-Sarhani. If you do that, you just look at exactly the same type of sum. d1 plus d2 is equal to k0 minus 2. And here you just have two disconnected components, but otherwise it's exactly the same as before. d0 k, d1 and d2 kb, and the same combinatorial factor. 2d2 plus 1 double factorial, and you divide by 2k0 plus 1 double factorial. You don't have any factor of 1/2 anymore because of the symmetry of the exchange of z and minus z. But now you're left with the case where g equals 0 and you've got two arguments here. And I give you the result. It's a sum over. You can have two arguments only when when A is just one element belonging to 1 to n. So it's a sum from I ranging from 1 to n of, and the result is this one, C. So what is left is CG with k minus 1 argument. So d1, so you make a sum over d1. K and the set 1 to n minus the element I. And now the constraint is that d1, you do exactly the same thing as before, except that you replace d2 by minus ki. So yeah, I will write the result directly. It's CG k0 plus kj, ki minus 1. So I remove one I here, so I remove the ki, and I put it together with the k0 with this row. And you've got just one combinatorial factor, which is 2 times k0 plus ki minus 1 double factorial. And you divide by the same factor, 2k0 plus 1 double factorial times 2ki minus 1 double factorial. So we started with the recursion for this specific curve, wrote down the residue formula in terms of coefficient of the expansion, and we get this recursion for the coefficient. So actually, this is enough to show that there is only a few of these coefficients which are non-vanishing. There is a constraint on the relation between the k and g, which makes that actually this omega gn are polynomial in inverse powers of this square. Because I want this to be interpreted to have a nice formula. So, no, the claim is that, and yeah, but so the claim is that I want to have that at the end of the day, this recursion, and I will discuss that later, I mean, next week, k1 to kn, g. You can write it as some integral over a moduli space, mgn bar, of a product from I going from 0 to n, of psi I to the power ki. And I didn't want to have the double factorials here. So in particular, if g equals 0, these are multinomial coefficients. And now I will, so one way to see it is to see that this recursion gives you exactly the definition of these numbers. Another way is to map it to what you would get by topological recursion on a matrix model, which is generating ribbon graph, which is exactly what Kontsevich has done in order to describe this integral in terms of ribbon graph. So you can map this to this point. And the last point is, I mean, I will discuss all that next week, is to say that actually this equation, you can think of it as say a differential equation of order 2, which is known as Virasor constraints. And I will discuss that next week. It's a very important point for the topological recursion. And I think I will stop here.